Okay, so now we're going to talk about the first aspect of IR spectroscopy signals, and that's the wave number, right? So the wave number is affected by two things: the bond strength, let me get my marker here, bond strength, okay, and the mass difference of the atoms, okay? So we're not going to do any calculations at all when we're doing these, but I want you to see where we get these numbers from, and they'll make some sense. And frankly, we're going to be able to drive a tremendous amount of information from a few factors, but I want you to be exposed to the real science behind it, okay? So the wave number is calculated according to the following equation, where this is the force constant right there, and that's essentially the strength of the bond, and this is the size of the atoms, okay? So the stronger the bond, the higher the stretching frequency, and the larger the mass difference, the higher the stretching frequency. All right, so again, we're going to probe that in more depth now. So the trends in stretching frequencies of given bonds can be rationalized based on bond strength and the mass difference, as we said before. Let's look at this. So if you have a hydrogen with a proton, it's called deuterium, right? And which is twice as heavy as hydrogen, right? And so the CH bond will absorb around 3,000 reciprocal centimeters, and a CD bond will absorb around 2,200 wave numbers. A CO bond will absorb around 1,100 wave numbers, and CCl is around 700 reciprocal centimeters. Okay, so CN triple bond, because it's a stronger bond, right, than this, will have a higher frequency. So a C triple bond N will absorb at 2,200. A double bond, which is weaker, at 1,600, and a CN bond at 1,100. Let's look, and that's you can see it's the size difference and the bond strength, right? So here's the size difference. That's the first one. The trends can be rationalized based on bond strength, no, mass difference, sorry. And then the bond strength, which is here, those are some examples of that. All right, so the wave number formula in empirical observations allow us to designate regions as representing specific types of bonds. So this is cool. If we have something with a hydrogen, it's typically anything with a hydrogen is typically from 3,000 to 4,000. Okay, carbon nitrogen is typically in this area. Triple bonds, right? Double bonds are typically in this area, and single bonds between CC, CN, and CO are down here, all right? Now, the region above 1,500, I said this in a previous conversation, the region above 1,500 centimeters, I would probably say below because it's down here, right, is typically called the fingerprint region, and we don't look at it, all right? There's got information there. It's clear, but it's not something that's going to be easy for us to extract much information from. All right. So where am I here? So because oh man, I'm sorry for the misprint here. Because they have the same type of covalent bonds. See, look at this. Right? They have all the same kinds of bonds here. CC, CH, 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 CC, CO, OH, right? So they have all the same kinds of bonds. Since that's the case, and IR tells us the kind of bonds or functional groups, right? Then we can't tell the difference between these two, right? So this is something that was very uncomfortable for me when I was first learning about spectroscopy. I always thought, all right, I'm given this spectrum, and it has all this information in it, and I'm going to have to be able to label everything and correctly identify the compound. And you're going to find that's not always the case. In fact, it's frequently not the case, right? Spectra have a very limited amount of information that they can give us. It just turns out that the information that they give us is super useful, so we make a big deal out of it, right? But these two spectra are the same, basically, because they have the same kinds of bonds in them. That's really interesting to see that. So now let's look at bond strength again. If we have an sp3, remember it's an sp3 to a hydrogen S. This is the kind of bond we have here because hydrogen is not hybridized, right? So this is a longer bond and it's weaker, okay? And since it's longer and weaker, it absorbs lower than these other two, right? So this is a carbon sp2 bond, right, to a hydrogen S, right? So this has more S character in it, so it's a stronger bond. This is a stronger bond. And since it's a stronger bond, it's going to absorb higher. And this is sp. Let me go, same thing, right? Carbon, sp, hydrogen S. So this is a larger portion of this bond is S character. So it's a stronger bond. It's closer to the nucleus, and it's going to give, and it's going to absorb even further upfield, 3,300. Okay, let's look at some examples of that. If we have an alkyl CH, that is, it's just a plain, right, sp3 hybridized carbon, it absorbs, look at right here, okay? If we have an alkenyl carbon-hydrogen bond, it absorbs, you see that? Up around 3,100. Or it's a little less than 3,100, I guess, right? So if we have an alkynyl, right, that's got more S character, it absorbs up even further yet. You see that? This, and this are evidence of what I showed you in the previous slide. Okay? Now, this is just as a side note, it's possible to have nothing upfield of 3,000 because you can have a double bond with no carbon-hydrogen bonds at all, right? It could be chlorine, 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 and chlorine, right? And no hydrogens on there at all, no carbon-hydrogen bonds, and so you don't have anything upfield of that, right? Okay, so let's look on resonance. Yes, okay. So another thing that affects where the wave number at which a bond vibrates is resonance. So resonance delocalization affects the strength of the covalent bond, and since it's the covalent bond is weaker because of resonance, the wave number changes. So look at this. This is telltale, okay? Big deal. I think I pointed that out in a previous conversation, that if you have a carbonyl bond in there, a carbon-oxygen double bond, you're going to have something close to 1,700 wave numbers. All right? Now, if it's conjugated, that means if you have possible resonance, right, where this can go here and this can go here, and you get this resonance stabilization, right? Right? There's our resonance stabilization, okay? Then all of a sudden we'd say, oh, that bond is weaker then, right? It's weaker, and so it's going to absorb below 1,700, right? So resonance destabilizes, and it affects the wave number accordingly. So here's this is what I just showed you. Sorry, I got a little ahead of myself. So this has only one kind of resonance. This has got a couple kinds of resonance, and so it makes it even more. It's resonance stabilized, yes, but that bond itself is actually weaker. Okay, pushing through, aren't we? Okay, we already said this, and I'm going to skip this slide. This is our last one. Okay, just to again point out that lower frequencies are observed when you have resonance stabilization. Right? Same thing goes for esters. So here's an ester group down here. First of all, in the previous slide, we did a ketone, but here, if you have an oxygen with more carbons on it, then you get the same thing. So an ester, typically, this particular one will absorb, let's say, at 1740. If it's conjugated, it'll be less, 1710. All right, so there's a brief introduction to the factors that affect the wave number of the signals that we observe in infrared spectroscopy.